Hello everybody. Today we welcome Andrea Santi again to our seminar. Andrea Santi from University of Roma. Last time he from the Norway, right?
Yes.
And today he shall give a talk on his recent is Boris Kruglikov on three non-degenerate CR manifold in dimension 7. So please, Andrea.
Thank you, Van, first of all, for the invitation. I think I was here more or less precisely 2 years ago, maybe a day more, day less, something like that. And yeah, at the time, I think I was speaking about
Super algebra.
Super geometry, yeah.
Yeah.
So the topic of today, let me see if I can, okay. So I've thought about the talk in three parts. The first part is kind of introductory for the problem of equivalence for CR manifolds and notion of holomorphic non-degeneracy in relation to, in particular, in relation to a filtration introduced by Freeman, and some overview of recent results, especially in dimension 7. And then I will focus on the locally homogeneous case, tell you a bit about a concept I introduced kind of 7 years ago called the universal CR algebra, and how I use these tools together with Boris Kruglikov to give a complete classification of locally homogeneous three non-degenerate CR manifold in dimension 7. And I will finish by telling you a bit about also globally homogeneous and how all this is related to a conjecture of Beloshapka. So let me start with the first part. So a bit of history of the problem. So more than a century ago, Poincaré realized that two generic real hypersurfaces in situ are not biolomorphically equivalent. And later on, Cartan realized that any such hypersurface inherits an intrinsic geometric structure given by distribution D, which is the maximal complex distribution, and the complex structure that comes defined on D, which comes from the fact that C2 has a natural complex structure. So he solved the equivalence problem for three-dimensional so-called Levi non-degenerate CR manifolds. And his construction in modern terms says that he constructed a bundle over M with an absolute parallelism in such a way that automorphism of your underlying CR structure corresponds in one-to-one fashion to automorphism above that preserve the absolute parallelism. So much after, the construction was generalized by Chern and Moser, still to Levi non-degenerate hypersurfaces, but inside any Cn, so n bigger or equal to 2. So they propose an approach for the construction of a system of invariants based on normal forms for defining the equation. But today I would like to mention briefly the approach of Tanaka, which in a sense put on modern terms what Cartan did. So the starting point is a manifold with a distribution D, and whenever you have such an object, you can consider sections of D, and you start enlarging by taking brackets. So sections of D will be the -1 term of your filtration. Then you enlarge by taking brackets of this distribution, which is in general not involutive, and you keep going. So you get a filtration of vector fields, and if you evaluate at a point, you get a flag. So you start from D-1x, which is just the distribution evaluated at a point, and you get this this nested sequence D-2, D, and so on. By dimensional reason, at some point is stabilized at a certain index. It needs to stabilize, and there's no loss of generality in assuming that it's stabilized at the full tangent space. So this is the filtered object, and you can pass to the nilpotent graded associated object. So that's MX. That's the graded vector space of TXM with this filtration. And commutator of vector fields induces a structure of nilpotent graded Lie algebra on this guy, and the depth is mu, the index where your filtration of the distribution reached the full tangent bounds. Okay, so the distribution is called strongly regular if actually we have a flag of distribution. So the rank of these object does not depend on the point. Okay, and the strongly refers that all these symbols, all these MX, are actually all of them isomorphic to a fixed M. To introduce the concept of a Tanaka structure, it's not really crucial for today, but just to give a little bit of context, you consider the bundle of graded frames. These are graded Lie algebra isomorphisms from M to MX. Tanaka structure is just a reduction of this principal bundle, a reduction PC. So in particular, CR structure can be encoded in this framework. And parallel, you have also the notion of Weisfahler maximal prolongation. So this was introduced independently both by Tanaka and Weisfahler. So you start with a non-positively graded Lie algebra. So in the negative part is your M, plus you have some G0, which are the algebra of 0-degree derivations of M. And the maximal prolongation is the algebra G infinity, possibly infinite dimensional, that extends your M plus G0. So the non-positive part has to be equal as your starting data. And in the positive part, you include everything that you can put, but without central elements, so to speak. So to make it more precise, if your X is in GK, and K is bigger than or equal to 0, but X trivially on G minus 1, then X has to be 0. Okay, this GK can be defined iteratively and realized as polynomial vector fields on M of a certain weighted degree. Parallel to this algebraic input, you have a geometric picture. So you have a tower that's a deeper construction. It's adding a lot of details, but you have a tower of principal bundles over M. The first one is your Tanaka structure P0, and then you on top of P0 you have some P1, and then P2 and so on. And your Tanaka structure P0 is of finite type if this tower stabilizes. From the perspective of the maximal prolongation, it just means that G infinity is a finite dimension. Okay, so Tanaka proved a very general theorem in this context, but let me say what's the incarnation in the case of CR geometry. So you start with MDJ, which is a strongly regular CR manifold with CR symbol MJ. So M is the symbol as I explained before, and J is just the complex structure on M minus 1 that is induced from the complex structure of your CR manifold. Set G0, all the 0-degree derivations of M that are compatible with J. And Tanaka showed that the dimension of the maximal prolongation is finite if and only if for every non-zero V in M minus 1, you have a W in M minus 1 such that the bracket is non-zero. So that's just another way to say that the Levi form is non-degenerate. If that's the case, you have a bundle P over M and a parallelism in such a way that the authomorphism group of your CR manifold corresponds to the authomorphism group of the parallelism. The latter is finite dimensional. P as the dimension of P is equal to the dimension of G infinity. So this gives you a bound on the dimension of your authomorphism group. And finally, it's not written on the slide, but if the authomorphism group reaches the maximum possible dimension, then essentially it's the so-called flat model. Your MDJ is locally isomorphic to the homogeneous model G mod H, where G is the Lie group corresponding to G infinity. and H is the subgroup corresponding to the non-negative part on G infinity. So G0, G1, and so on is the stabilizer. Oh, so let's give an example. So here is the strictly pseudo-convex hypersurface case. In this case, the strongly regularity assumption is automatic. The absolute parallelism is actually a Cartan connection with values in SU n plus 1, 1. The flat model G mod H is, as you probably know, is the sphere. Tau as the projectivization of the null cone in Cn plus 2. G is the special unitary group, and H is the stabilizer of an isotropic line. In this case, the model is locally isomorphic to a cube over a certain hyperquadratic, which is written at the bottom of this slide explicitly. Okay, so a lot of effort has been done in the last year to classify locally homogeneous Levi non-degenerate CR hypersurfaces. In dimension 3, this was done by Cartan, and in dimension 5, it was finally settled 2-3 years ago by Loboda and Dubrov, Merker, Medvedev, independently and using different methods. So one of the simplest example of CR manifolds that are not Levi non-degenerate are just products of smaller dimensional CR manifolds with complex manifold. But these are kind of trivial example, and any CR manifold that is of this form locally, we say that it can be locally straightened. An example which is well known to be a Levi degenerate CR manifold that cannot be locally straightened is the so-called cube over the future-like cone. So that's a cube in C3. It is Levi degenerate at all points. If you want to check these, it's easy to consider the completion of M inside CP4. This is homogeneous for the special orthogonal group in signature T2. So you just need to check at one point Levi degeneracy. And it's also foliated by complex leaves, since the future-like cone is a union of real half lines. So the cube is union of complex half line. Nonetheless, this example admits no CR straightening. So this can be seen by the so-called necessary condition, which under real analyticity assumption are also sufficient, actually, as described by Freeman. So let me tell you what is the sequence constructed by Freeman in the 70s. So that's, again, a filtration. You start from f minus 1. So throughout the talk, if I'm dealing with filtration, the index will be up. If I'm dealing with the associated graded objects, usually the index will be down. So this is a sequence of complex vector fields. FP splits in 1, 0 and 0, 1 part. The 0, 1 part is just the conjugate of the 1, 0 part. And it's defined iteratively. So if you look at f minus 1, 1, 0, these are just the 1, 0 sections of your distribution. And then you define fp10 as the elements in fp minus 1, 1, 0, such that when you hit it with d01, so you do an anti-holomorphic bracket, this has to land in fp minus 1, 1, 0, d01. An alternative way to look at fp10 is at the bottom, the last bullet point. This is just the kernel of higher order Levi forms. So how they are defined, you take fp minus 1, 1, 0, tensor d01, you do the bracket, you quotient by the direct sum of the spaces where the entries live in, and this is a tensorial object, and if X is in the kernel of this tensor map, then it belongs to fp10. So of course, f minus 1 is all the sections of D complexified. And it turns out that for p bigger than or equal to 0, fp is actually a Lie algebra of complex vector fields. So we have two filtrations at hand, the one coming from Tanaka and the one coming from Freeman, and we say that our CR manifold is regular if essentially we have a constant rank assumption. So this filtration of vector fields really corresponds to bundles. So we have a flag of distributions, okay? So in the locally homogeneous case, this is automatic, and in the real analytic case, this is also automatic upon localization by upper semi-continuity. So depending on which questions you are interested in, that's not really a strong assumption, okay? Let me point out that F0, or rather its real part, if you wish, is the Cauchy characteristic distribution. So these are the sections of D that sends D into D. So this is just stable and involutive. Its maximal leaves are complex manifold, but the existence of, or rather the absence of local CR straightenings comes from the following definition of K non-degeneracy. MDJ is called K non-degenerate if well, this Freeman filtration has to stabilize at some point. And we say that is K non-degenerate if it stabilizes to 0 at index K minus 1, okay? Otherwise, if it stabilizes but to something non-zero, we say that it's holomorphically degenerate. So that's the definition given by Freeman. There is also one without the constant rank assumption, and you can find it in Bauwendi Ebenfeld Rothschild book. Here you see the celebrated result on Felsted-Kaup about the classification of all locally homogeneous two non-degenerate CR manifolds in dimension 5. They are all tubes over surfaces in R3. You have 5 families, and the first one is the future-like cone example that I mentioned to you before. That's the maximally symmetric one inside the class of two non-degenerate locally homogeneous hypersurfaces. And all the other 4 cases are actually simply transitive. So the algebra of infinitesimal CR transformation has dimension 5. It's actually solvable. And if you look at the last example, it's constructed out of the twisted cubic, the rational normal curve of degree 3. And that will play a role also in my results with Boris. So a lot of efforts has been done in the last year to construct absolute parallelism for two non-degenerate CR surfaces in dimension 5. This was done by Isaiah Zaitsev, Medori Spiro, Merkel Pocchiola. Later on, the question on whether this absolute parallelism is a Cartan connection was addressed by Gregorovich. And more recently, yes?
You say that a tube over surface, so that is not a direct product. What is the IR3 here? So that is a changing over surface? Tube S plus I E R3.
Well, you have a, so S is in R3, it's just on the real part.
S and
so
3.
Whereas the imaginary part is free. You can take
So that means a direct product of the surface.
Yeah.
Okay.
Yeah. And I was saying, yeah, and Kosovsky-Koller recently gave a complete normal form for such CR manifolds. Let me jump to the two non-degenerate 7-dimensional case. So we are moving towards the 7-dimensional case. Back in 2015, I introduced the concept of bigraded CR symbol for K non-degenerate CR manifold. At that time, I call it core, but it's clear that later on in the literature, this concept has been used many times, and bigraded CR symbol is kind of established nomenclature now, and I think it's actually better than the name I gave at that time. and also universal CR algebra. So I will tell you about these two concepts. At the time, I used these tools to construct a 7-dimensional two non-degenerate homogeneous model. It was clear already at the time that the moduli space of such CR symbol contains continuous parameters, contrary to the Levi non-degenerate case, where they are just distinguished by the signature of the Levi form, so it's discrete, and that there exists CR symbols that do not admit homogeneous model. Then the construction of absolute parallel has been obtained by Porter and Zelenko, and concluded by Sikes and Zelenko very recently, using very deep modification of Tanaka prolongation scheme. Recently, Sikes also classified the 7-dimensional two non-degenerate homogeneous model. There are 9 of them. 6 correspond to what I found back in 2015. But there are additional such models because he uses a slightly modified notion of bigraded CR symbol, which encodes a bit more of information. So there are some models that collapse with the same bigraded CR symbol, but with respect to the modified bigraded CR symbol, they are different. But, okay, I don't want to go into many details. Beloshapka showed that the upper bound for dimensional symmetry algebra of two non-degenerate 7-dimensional CR hypersurfaces is 17, using a modification of the homological technique of Poincaré. Recently, Sikes and Zelenko further refined this estimate to 16 and found a bound attained by the hypersurface, which is shown here in this slide. I have to mention that this upper bound 16 is in the case of when this modified bigraded CR symbol is constant. So it certainly includes locally homogeneous CR hypersurfaces, but a priori there might be lurking around an example with non-constant modified bigraded CR symbol and 7-dimensional symmetry algebra. Although this is perhaps unlikely, such an example is not ruled out and is unknown at the same time. Okay, so let's finish this first part with Beloshapka conjecture. So about 3 non-degenerate CR manifold, the lowest manifold dimension for which such CR manifolds with this order of non-degeneracy can exist is 7. In 2021, Beloshapka found the upper bound for the dimension of the symmetry algebra of these hypersurfaces to be 20. And in my result today, I will give with Boris a finer estimate in particular. But the point is this, all these results support the conjecture stating that CR hypersurface with maximal finite dimensional symmetry algebra are the Levi non-degenerate ones. So this is the conjecture of Valeri Beloshapka, and he says that if you have any real analytic and connected holomorphically non-degenerate CR hypersurface with CR dimension n, the dimension of the algebra of infinitesimal transformation is bounded by n squared plus 4n plus 3. And the maximal value is attained only if m is spherical. So if any of its points has a neighborhood which is CR equivalent to the flat model for the non-degenerate case. Okay, let's jump to the second part. So I want to tell you what a bigraded CR symbol is. So you find definitions in the literature, they are equivalent. Back in 2015, I introduced it in the following way. So that's a finite dimensional real vector space, M, which is now graded, but not necessarily only in negative degrees. So you see you have your MP with P ranging all over Z. And it's endowed with a complex structure J compatible with the grading. And J is defined not only in M-1 as before, but also on M0, M1, and so on. The CR symbol, the bigraded CR symbol is not a algebra in general, its negative part is. So if you take its negative part, you have a bracket of the algebra that is compatible with J, and which is non-degenerate in fundamental in Tanaka's sense. Non-degenerate, I just mean that the condition I mentioned before in Tanaka theorem holds. And fundamental just means that n-1 generates all the negative part. Third property, let's say from now on, I will often denote complexification of vector spaces by a hat to save space. So your MP hat splits in 1, 0 and 0, 1 part. And using the bracket, you can look at n-1, 1, 0 as a space of maps from n-1, 0, 1 to the complexification of n-2. That's just the fact that the bracket of n-1, n-1 into n-2 is compatible with J. And what remains of the higher order Levi forms defining Cannon degeneracy, passing from the filtered to the graded level, is these maps that are defined at point 3. So you have some injective linear map from MP10 that gives you a morphism which takes as an input elements of n-1, 0, 1, and it gives you something in M P-1, 1, 0. So it's compatible with Z degree, and it's kind of anti-holomorphic component of the bracket. Since you land in M P-1, 1, 0, you can iterate these and starting saturating entries with more elements of n-1, 0, 1. And if you do that, this has to be symmetric in your entries. Okay, the point is that if you start with a Cannon degeneracy R manifold, such that D minus mu is your full tangent bundle, then you can consider a Z-graded real vector space defined in the following way. If P is less than or equal to -2, you take the quotient coming from the Tanaka filtration. So you do dP modulo dP plus 1. And if P is bigger than or equal to -1, MP is actually the quotient of the Freeman filtration. So you do FP modulo FP plus 1. And you evaluate all of these at the point. In this formula, you see that the index ranges from less than -2 and more than -1. But actually, if you take -1 in the first formula, they overlap. So they give you the same result. Okay. So taking the higher order Levi form give you a natural structure of bigraded CR symbol of depth mu and height k minus 2. So now the height is not -1. That's the case when k is equal to 1. And in that case, the bigraded CR symbol reduces to the usual CR symbol for Levi non-degenerate CR manifolds. Otherwise, you have contributions also in non-negative degrees. Okay, so from now on, I want to restrict to CR manifolds of hypersurface type. So that means that the negative part of the CR symbol is the Heisenberg algebra. And to arrive at the definition of universal CR algebra, I need two ingredients. CR algebra, first of all, which are the Lie theoretic counterpart of locally homogeneous CR manifolds. And I need to tell you about the infinite dimensional contact algebra of Weisfeiler. So first of all, CR algebras. These are pairs, GQ, where G is a real algebra. Q is a complex subalgebra of the complexification G hat of G. And third requirement, you ask for the quotient of your real algebra G modulo the stabilizer to be finite dimension. The stabilizer, by definition, this is, let's say, at a purely algebraic level, but I will make contact with geometry soon. The stabilizer is defined as the intersection of G and Q. And it is also the real part of Q intersected with Q bar. So this notion was introduced by Medori and Nacinovic in 2005, and together also with some improvement by Feltz in 2007. They show that if you have a CR manifold or a germ of it at a fixed point, which is locally homogeneous, then you have a naturally associated CR algebra GQ, where G is all the infinitesimal transformations of NDJ, and Q are the complexified symmetries, so element X in G such that if you evaluate your fixed point X, they land in D10. Conversely, if you have an abstract CR algebra, this determines a unique germ of a locally homogeneous CR manifold, such that the tangent space at X can be identified with G modulo the stabilizer, and the fiber of D10 is Q, and you have to quotient with the elements of Q vanishing at the origin, so with a complexified stabilizer, which is Q intersection Q bar. Here you see the picture of Weisfeiler contact algebra. So that's it's an infinite dimensional graded V algebra that geometrically are the infinitesimal automorphism of a contact manifold. So C minus 2, C minus 1 is the Heisenberg algebra, C0 is the conformal symplectic, is isomorphic to the conformal symplectic transformation of C minus 1. That index should be down. I apologize. And here in this slide, I'm using the notation that the K-symmetric power of C minus 1 is just written as Sk. So what are the graded components of the Weisfeiler contact algebra? In degree minus 2, you have just R, which is S0, the zero symmetric power of C minus 1. In minus 1, you have C minus 1, so the first symmetric power. In degree 0, you see S2 and S0. S2 correspond to symplectic transformations and infinitesimal ones, and S0 to the grading element. In degree plus 1, you have a copy of S3 and S1. In degree plus 2, of S4, S2, and S0, and that's the general pattern. At degree P, you start with SP plus 2, and you move to SP, SP minus 2, and so on, until you stop. Here in green, you see the adjoint action of C minus 2 that lowers the degree by 2, right? So for example, you have an S0 in degree plus 2 that will go to the S0 in degree 0 and then to the S0 in degree minus 2. Whereas the adjoint action of C minus 1 is in red. And so you just go down by 1 degree. And for example, if you look at the S2 in degree 2, the C minus 1 is in S1. So you can land in S3 and in S1. From a theoretic point of view, and that's what happens. And similarly for the others. Okay, that's just a glimpse of the algebra structure of the Weisfeiler contact algebra, because then you need all the brackets that do not involve the negative part, but that's enough. So you can by grade the Weisfeiler contact algebra. So you take a complex structure in C0. So that's a complex structure acting on C minus 1. Compatible with the bracket. That was our setting.
Andrea, could you explain me that is a Weisfeiler contact algebra abstracting, right? Not related to contact CR manifold or?
The Weisfeiler contact algebra is the symmetry algebra of a contact manifold without any CR structure involved. But now I'm introducing a complex structure in degree 0. J, and that will give an extra grading, because you can take the eigenvalues of J on each of the pieces of the Weisfeiler contact algebra, are here written in red. I didn't write the imaginary units for simplicity. And so you see that, for example, in minus 1, you have the eigenvalues plus I and minus I, of course. And in degree 0, the eigenvalues range from 2i, 0, and minus 2i. So the Weisfeiler contact algebra is the symmetry algebra of a contact manifold, but without any complex structure involved.
So that means that for any CR manifold, you have associated contact manifold, or only?
Yeah, I'm arriving to this.
Okay, thank you.
Yeah, just a sec. Yeah, thanks. And then you see the eigenvalues at level 1. They will that will be the action of J on S3. So the eigenvalues will run from 3i, I, well, not 0, I should remove that 0, minus I and minus 3I, and so on. So that gives a bigrading on the bispheral contact algebra, or if you want, on its complexification, because these are imaginary eigenvalues, and which is compatible with the liberated. So I define the universal CR algebra as follows. So that's a CR algebra. So it's a pair. As I said, the first one, it has to be a real algebra, and the second one has to be a subalgebra of the complexification. So the real algebra is the bispheral contact algebra. And the subalgebra of the complexification, which I call it U for universal, is that at each grade, at each Z degree, you take the J eigenspaces, all the J eigenspaces except the one corresponding to the minimal eigenvalue. So except the one that are in red. All the p's in green, so all the eigenspaces corresponding to the green eigenvalues, it's what constitutes the complex subalgebra U of Cn. So formally, this universal CR algebra is holomorphically non-degenerate. It has a Z bigrading, but bear in mind that if you do C modulo the stabilizer, this is infinite dimension. Okay, so doesn't really fit the previous scheme. It's kind of formal analog. One can work with it, and it's useful because any abstract bigraded CR symbol of hypersurface type admits a natural immersion in the universal CR algebra. Not giving you much details about this immersion, but the point, at least one of the point, is that I use it these two properties to construct a CR algebra, GQ of the universal CR algebra CU, that is the symmetry algebra of a locally homogeneous model for three non-degenerate 7-dimensional CR hypersurfaces. So in general, construct hypersurfaces that are K non-degenerate at some points, but Levi non-degenerate on a dense open subset is not too difficult. It seems much harder to construct CR hypersurfaces which are everywhere K non-degenerate. So let me give you the examples of the previous examples. So the strictly pseudo-convex case as a CR subalgebra of the universal CR algebra. So here you see in red and green all the J eigenspaces of the universal CR algebra up to the degree plus 2, Z degree plus 2. And in green is the symmetry algebra of the strictly pseudo-convex flat model, so the CR sphere. So you see that in degree 0, it stays away from the extremal eigenvalues 2i and minus 2i. And in degree 1 as well, it stays away from 3i and minus 3i. And in degree plus 2, that's the same. So that essentially corresponds to the fact that this is Levi non-degenerate. If you actually have a look at the cube over the diffusion-like cone, you will see that in degree 0, you will get all the degree 0 derivations. So you will have those with J eigenvalue 0 that corresponds to holomorphic transformation of C minus 1, but also those with extremal eigenvalues 2i and minus 2i. And that's part of the tangent. It's not in the stabilizer. And since the tangent arrives up to degree 0, this corresponds to the fact that the cube of a diffusion-like cone is 2 non-degenerate. So let me finish with the model I constructed in 2015. So in this case, you have just one abstract CR symbol for the 3 non-degenerate 7-dimensional case. It's here. So you have 1-dimensional m-2 and 2-dimensional m-1 and 0 and m1. Let's denote a basis of the complexification of m-1 by z and z bar. And I will drop in the following theorem the symmetric product symbol to denote elements in the symmetric power of the inside the universal contact algebra. Then I constructed a Z-graded 8-dimensional Lisa algebra of C with components well in degree -1 and -2. That's everything you have in the contact algebra. GP is 0 in degree strictly bigger than 1. And in degree 0 and 1, it's written explicitly here. It's not so important. That Z is the grading element with respect to this grading. M is an element in G0, which is written here, and you see that it has this Z square component that tells you that you have a non-trivial projection onto the 2i eigenvalue. And here you have an N, which is of this form, this complicated form, but the point is that you have a Z cube. So it projects non-trivially to the 3i eigenvalue. So this is 3 non-degenerate, and it's a CR subalgebra of the universal CR algebra. So the Q, I told you what is G, and now I'm telling you what is Q. The Q is just obtained by intersecting the U of the universal CR algebra with the complexification of G. So this pair GQ is the algebra of infinitesimal CR transformation of a 7-dimensional 3 non-degenerate homogeneous CR manifold. So before moving to the third part, let me answer also to one question. I will be back to this later, but if you take your CR manifold with a certain order of K non-degeneracy and you quotient by the Cauchy characteristic space, then at least locally you can consider the space of leaves of this foliation, and this is a contact manifold. And by K non-degeneracy, your algebra of symmetries of your CR manifolds is projectable downstairs to this space of leaves, and it's projectable in a faithful way. So you do not lose information by pushing your symmetries down to the contact leaf space of the Cauchy characteristic space. We use this fact. I'll be back on this in a second. Let me first mention that together with Boris Kruglikov, so I'm now turning to the recent results. We recently shown that the abstract model I derived in 2015 is also a cube, which we call it R7 inside C4. So to realize it, you have to do it like this. You consider the twisted cubic, which is a projective curve in RP3. You consider the cone R over the twisted cubic, that's a surface in R4, and you take the tangent variety to this cone. So that's not 4-dimensional, that's 3-dimensional, because the direction corresponding to the fact that R is a cone already belong to the cone. So you are not increasing by 2, but you are increasing dimension by 1. So this sigma is 3-dimensional hypersurface in R4, and here you can see an explicit parameterization, but it has also some global defining equations. So these formulas nicely match and actually give a geometric interpretation to an example found by Fels and Kaup in 2008. In order to find the model R7, you consider the orbits on R4 of GL2R. You have to think of R4 as 3R2 with the natural action of GL2R. And the tangent variety is GL2R stable, and inside there you have 3 orbits. The regular part S is the complement of the cone R inside the tangent variety. Then you have the puncture cone, and then you have the vertex of the cone. These are the 3 orbits. And the theorem is that the 7-dimensional 3 non-degenerate model is given by the cube over the regular part. So over this sigma minus R. This is a globally homogeneous CR manifold, diffeomorphic to S1R6. The topology, in other words, we are saying that the topology comes precisely from the twisted cubic which is S1 from a topological point of view. And its automorphism group is not connected, is GL2R semi-direct product S3R2. So the GL2R is the symmetry of the twisted cubic, that is also the symmetry of the regular part of the tangent variety. And the S3R2 are the imaginary translations. Okay, so the theorem, main classification result, recently on arXiv. There exists a unique locally homogeneous trinon-degenerate CR manifold in dimension 7. So any such structure is locally isomorphic to the model, R7. If you want to think about globally homogeneous one, every connected globally homogeneous trinon-degenerate CR manifold in dimension 7, the automorphism group of maximal dimension is a finite or countable covering of the manifold. Of the model R7. So the homomorphism group is the universal cover G tilde of G, or a quotient by a subgroup isomorphic to NZ of the maximal discrete normal subgroup of G tilde, which is isomorphic to Z. So a few words about statement 2, and then I will tell you more about statement 1. So the key point for statement 2 is that if you consider the exact sequence, where here you have the stabilizer, here the maximal discrete normal subgroup of G tilde, and here you take the counter image of the stabilizer in G tilde, so that's stub tilde. This sequence of this exact sequence of group actually splits. So stub tilde is isomorphic as a Lie group to the stabilizer product Z. Using this, you can obtain all the homogeneous model as quotienting G tilde by this MZ, which is a discrete normal subgroup. And then you take a stabilizer, the same stabilizer as the one we started with on the homogeneous model, taught inside G tilde, right? Because this sequence split. And equivalently, that's G tilde modulo stabilizer cross MZ. So this subgroup of the counter image of the stabilizer. If M is equal to 1, here we are quotienting G tilde with all the maximal discrete subgroup. So you land with G modulo the stabilizer, so you get back the homogeneous model. If M is 0, we get G tilde modulo stub, which is the universal cover of the model. So let me tell you in what remains a few words about how we obtain this uniqueness result. So the point is that you have to play with the two filtrations, the one of Tanaka and the one of Freeman. So since MDJ is locally homogeneous, the Freeman bundles are locally homogeneous as well, and the fiber of FP10 at the point X is isomorphic to some QP modulo the complexified stabilizer, where QP is a sequence of complex subalgebras of Q introduced by Fels. So the point is that these are the complexified symmetries whose value at the point is in FP10, and this can be defined also in purely theoretic terms. I don't want to spend a lot of time on this definition. Is really the Lie algebraic counterpart of the Freeman sequence in terms of complex subalgebras of Q. So if you take QP plus Q bar P, these are the, let's say the real part of this. These are the symmetries whose value at the point is in the Freeman bundle FP. And this is a Lie subalgebra of G. So we have a kind of compatibility condition between these Qs and the Lie structure. But one key point is that the filtration QP is actually not respected by the Lie brackets in general. So if you do Q1, Q1, this will not land, for example, in Q2. The other filtration you have to work with is what we call contact filtration. So this comes exactly from the fact I mentioned before to Van Le. That if you are in the Cannon degenerate situation and you take the leaf space of the Cauchy characteristic space, this is a contact manifold, and your algebra of symmetries projects faithfully as a Lie algebra of contact transformation of the leaf space. So you have a natural filtration then downstairs from the contact point of view, and you can reread this filtration upstairs directly on G. And it's defined as follows. G minus 2 is all of G. G minus 1 are the symmetries that takes values in D. So far, it coincides with the traditional filtration introduced by Weisfaller and Morimoto Tanaka to study the algebras of vector fields. But then from level 0 on, they start to diverge. So for example, G0 are all the elements in G minus 1 that sends G minus 1 into G minus 1. In general, this G0 is bigger than the stabilizer. Okay, so this is one of the properties. This filtration is compatible with the bracket. So if you do GP, GQ, you land in GP plus Q. And then you have an additional kind of compatibility condition of the contact filtration with the Freeman-Felts subalgebras Q. So if you take QP plus Q bar P, this coincides with the complexification of GP, but only for P minus 1 or 0. That's rather easy to see. From P bigger than or equal to 1, then you can only say that G at P is contained in the sum of these two guys. So in particular, you have this equality, G at 0 plus the complexified stabilizer, that's G at 0, because the stabilizer is inside G0. And that's also equal to Q0 plus its conjugate. But from P bigger than or equal to 1, you can only say that G at P, even if you add the stabilizer, it's only contained in QP plus the conjugate. So requiring the opposite inclusion is equivalent to ask that if you have an element in QP plus Q bar P, that means a complexified symmetry that takes values in FP, in the Freeman bundle P, then there is a symmetry at level, contact level P, that has the same value. So in other words, if you take the valuation map from the contact filtration component GP to the fiber of the Freeman bundle FP at X, this is surjective. So we thought for some time that under some condition, this was true. But actually, we found a counterexample in dimension 9, and that's the tricky point that Ong Van Le was mentioning before the talk started, that it required a kind of work to deal with this case, namely when this evaluation map is not surjective. So let me, before moving on, let me stress these notable differences between the two non-degeneracy and higher non-degeneracy case. So from T non-degeneracy on, the Freeman sequence relies both on the distribution and the complex structure. Instead, in the two non-degenerate case, the only object you have at hand is the Cauchy characteristic distribution. And that's intrinsic to D. It doesn't depend on J. And that makes life a bit easier to a certain extent. And the other point is that describing K non-degeneracy of a CR structure at the filtered level, one would like to assign non-negative degrees to the vector of the Cauchy characteristic distribution. However, that's exactly this fact that this evaluation map is not surjective in general. From T non-degeneracy on, elements of filtration, of Freeman bundle FP with P bigger than or equal to 1, one ideally would like to see them at the contact level P and so on. But unfortunately, they also have non-trivial components of filtration degree strictly less than P. So this in the two non-degenerate case doesn't happen. You cannot see this phenomenon. And that's a notable difference between two non-degeneracy and higher non-degeneracy. Let me skip the counterexample in dimension 9. Maybe I can go back later if someone is interested. So to arrive at the result, what we had to investigate is the passage from filtration to gradings. So you have your CR hypersurface, locally homogeneous and K non-degenerate. and G is the infinitesimal transformation. And as I explained, you have a natural contact filtration in here. So you can pass to the graded of G, and this is a graded subalgebra of the contact algebra C. Okay, so you lose information, but only because you are passing from the filtration to the grading, not because projecting to the Leaf space of the Cauchy characteristic space as some kernel. Moreover, your complex structure at a fixed point X induces a complex structure J on C minus 1, and you can use this to construct the universal CR algebra. So the point is that graded of G is inside C, and if you look at the graded component, so GP, let's say complexified, this is in CP complexified, and CP splits in UP and the eigenspace of minimal eigenvalue. So here it's the by grading is written explicitly. This first P refers to the Z grading, and this minus P minus 2 refers to the grading coming from J. So the aim is that one would like to constrain, first of all, these graded components. And these are the general results that we used. So let's assume we have a symmetry contact filtration P. Take the equivalence class V. So this is in GP with the index down. Then, well, first of all, your symmetry is in QP plus its conjugate. This is something we already stated. And, well, it is in level P plus 1 with respect to Q bar, if and only if the principal part, V, is in UP. So if and only if the principal part of your vector field stays away from this minimal eigenvalue inside the universal CR algebra. This also holds for the conjugate for QP plus 1 instead of Q bar P plus 1. And if you take the two statements together, you obtain that C is in Q plus 1 P plus Q bar P plus 1, if and only if its principal part stays away from the extremal eigenvalues. And that's what makes life a little bit more complicated, because in the model that I showed you before, everything that stays away from the extremal eigenvalues is actually part of the stabilizer. But in general, you cannot say this. You can say that it's not in QP plus Q bar P, but it's in Q plus 1 plus Q bar P plus 1. And as a corollary, if you have a symmetry which is at contact level Q, but not at contact level Q plus 1, then this will be, sorry, oh gosh. If you take a symmetry which is in QQ, but not in QQ plus 1, this is then this is a contact level P for some maximal P which is less than or equal to Q. In the say nice case, when this P is really actually equal to Q, then the principal part of your vector field is non-zero and is in UP, but not in UP intersection UP bar. So what it's going to say? That is non-zero, it has a non-trivial projection to the maximal eigenvalue. So it really gives a strong constraint. On the other hand, in the not nice case, so if P is strictly less than Q, then the principal part of your vector field of your symmetry stays away from the extremal eigenvalues. Okay, so let me maybe skip this definition. So we gave some condition for which the evaluation map that I mentioned before is surjective, and we call this an alignment condition. So that builds on trivial filter deformation. So you first ask that G from the filtration and grading level is the same with respect to the first gradation. And alignment is a requirement also of stronger compatibility condition from the complex point of view. In the case when G is aligned, then you get a situation similar to the homogeneous model I showed you before. So Q is just U intersection G hat. You have equality instead of inclusion in what I mentioned before. So G hat P plus the complexified stabilizer is actually equal to Q3 plus its conjugate. The complexified stabilizer subalgebra is Z-graded. So you really need, in this aligned case, a very nice picture. But in general, that's not the case. So what we need to do to prove this uniqueness result, here is the step of the proof. First step, you show that your trinomial degenerate CR manifold is either locally CR diffeomorphic to the model, or its symmetry algebra is 7-dimensional and it's a filtered deformation, not of GL2R semi-direct product S3R2, which is the symmetry of the model, but of a cell2R semi-direct product S3R2. Then you show filtration rigidity, no such non-trivial deformations are possible. And after that, you show that such trivial deformations are always simply transitive subalgebras of the model, of the symmetry algebra of the model. Either because you show that such trivial filter deformation are also aligned, so there is this extra compatibility condition with the complex structure, or, and this is was kind of a technical point, you have some the algebras which are putative new examples, but with some work you actually have to show that they are conjugate CR subalgebras of the CR algebra of the model. So they look like they might be new example, but actually they are just the model in disguise. In the first step, one has to distinguish the analysis in 3 cases. You consider the evaluation map from the contact filtration at level 1 to the fiber of the Freeman bundle F1. This is 2-dimensional. So this evaluation map can have rank 0, 1, and 2. And depending on these 3 possibilities, you get rather different analysis. Okay, let me finish with the last slide. I'm a couple of minutes out of my time, but this is really the last. So in part 2 of the preprint with Boris, which should be on archive in the next weeks, we show that the symmetry algebra of any 3 non-degenerate 7-dimensional real-analytic CR surface, so not necessarily locally homogeneous, the symmetry algebra is dimension bounded by 8. So the previous bound was the one found by Valeri Beloshapka, and it was 20. So this is a big drop, and the bound is sharp. 8 is realized by the model that I just explained to you today. And the next realizable symmetry dimension is actually 6. So you don't have anything with 7. It's not written here in the theorem, but that's something we have. The proof uses various techniques from differential geometry, the theory, different notion of Tanaka prolongation. And in fact, we had to treat the intransitive case in a completely different manner from the transitive case presented today. So for some reason which is still not completely clear to us, if you consider the contact filtration, but in the intransitive case, that doesn't work so good with respect to other filtration. Perhaps this is due to the case that for the usual filtration of Tanaka and Morimoto, you have some stronger results about regularity at certain points, and this is not yet been established for the contact filtration. Maybe it holds, maybe not, we don't know. But it prevented to use the contact filtration also in the intransitive case, essentially. Okay, thanks for your attention, and sorry if I stepped a bit out of time.
Yes, thank you very much, Andrea. Really very impressive work, and you go over time because I interrupt with a few questions. Yes.
Yeah. Okay. Thanks.
Yes. So that contact structure on the you have such only for the case of the non-degenerated CR manifold. You have the correlation on the base is locally contact manifold.
Yeah, that's
All
correct.
this space.
Yes, yes. The point is that the contact structure doesn't project down, of course.
Yeah.
For example, in the two non-degenerate case, Sikens and Zelenko show that the contact structure essentially, if you take a point downstairs, you have your leaf up, moving your point in the leaf will give you a family of complex structure downstairs. So they call it dynamical CR Lagrangian structures downstairs.
So that the people already discover and they use it before. This is a contact structure, yeah.
Sure. I mean, it depends. It depends on how much information you want to retain when you go downstairs.
Yeah.
That's the tricky point. And in our case, it's essentially it's this technical part here that when you go down, you want to see what remains of your complex structure going down, and you can see these in the principal part of your vector fields, and they have this very different behavior depending on whether this principal part lies at a contact level, which is what you would like to, so coinciding with the Freeman level. But if actually is smaller, then you get something which, to a certain extent, one would like to think as a stabilizer, because that's what happens in the models, but that's not always the case. And actually, the scarcity of example made these quite obscure at the beginning. For a long time, I thought that at least for trivial filter deformation, then the complex structure was also aligned. But then we computed this symmetry algebra of these four non-degenerate CR manifold in dimension 9. That's an example in the paper of Fels and Kaup, but the symmetry algebra is not explicitly computed. So we did the contact filtration and so on. And we discovered that there are elements, this H tilde, which is in Q1, but well, okay, I'm not going into much detail, but this H tilde is it's a Cartan element in GL2R, and H is the Cartan element in GL2R, and H tilde is a slight modification. But the point is that this H tilde is in Q1, but its principal part, which is H, actually is in G0. So yeah, I think it would be nice to have a bigger pool of examples of local homogeneous CR hypersurfaces with K non-degeneracy in the minimal possible dimension, for example. Because Medori and Nacinovic constructed some examples of any K non-degeneracy, but in dimension 2K plus 3, not in dimension 2K plus 1. And for them, and for their example, actually, this aligned condition holds. So up to my knowledge, this is the only non-aligned example we have at hand. And a couple of non-aligned examples also came out of our classification, but it turned out a posteriori that they were just the maximal symmetric model in disguise. So yeah, I think from my perspective, having a bigger pool of example would really help the intuition, because so far they are really scarce. It's difficult to construct.
Is there some more questions? If there are no more questions, so let us thank the speaker. Yeah, again. And then, okay. So thank you.